speaker this morning is Patrick Dorry, and he's going to tell us about encoding the Bethe ansatz in ordinary differential equations.
Okay, so thanks very much, and thanks to all the organisers and all the Institute people. It's all been fantastically well arranged. Yeah, I realise that the problem with transparencies is the smallest bit of guck then shows on your transparencies in an unpleasant way, but this one was actually written at some point early this morning. It's not recycled yet. So yeah, I'm going to talk about what's said there. It's a sort of strange link between Bethe ansatz and differential equations, and I've talked about this to various of you at various times before, so I'm going to try and have something new at the end, but which is actually an article that was on the net this morning. At least it was there at about 3 o'clock this morning. Whether it's still there or not, I'm not sure, but it was there then, which was with Claire Dunning, Nando Gliozzi and Roberto Tateo, and Davide Masuero and Junji Suzuki are two other people we've been working on this quite a lot before. So yeah, so Paul Fendley kind of stole my opening lines a little bit, so I was going to say, you don't have to be ashamed about the Bethe ansatz anymore, but he said all that, so that's fine. I can get on with...
Do you have something about E8?
Not this time, actually, no. That's a big shame. Yeah, so rather optimistically, this is the plan, but whether I get through the whole lot is not clear. So first of all, I'll say a bit of general stuff about what I need from the Bethe ansatz. In particular, actually Volodya gave a good preparation for this. The idea that Bethe ansatz is well treated by looking at sets of rather discrete-looking functional equations. Okay, and in particular TQ, which you saw a bit of yesterday. And also, actually, for the sort of final bit of my talk, I need to tell you a little bit about what fusion hierarchies are. So I'll say something about that too. Then we'll switch and we'll talk about ordinary differential equations for a bit. And of course, the big thing is going to be that these same functional equations crop up in the differential equations. And that turns out to be rather useful and also rather intriguing. And the third bit, if I get time, I'll try and show the sort of role of minimal models in all of this. So you know there are these rather special conformal field theories, versions of rational conformal field theories, and in particular the C<1 rational conformal field theories, these things called minimal models, which everybody learned about when they're reading Belevin-Polyakov's Analogikov way back when. And it's kind of interesting to know where that crops up. And so you've got to keep listening because you've got to find out what the connection is with junk food, because there's a slight connection, which I'll probably not, again, get time to say. Good. Okay. That'll make you read the paper, but actually you won't find it out from the paper, so you'll have to ask me. Right. So, sort of in danger of blowing away. So, very quick thing about the Bethe ansatz, which we've had in, I think, 5 talks have Bethe ansatz in their title in this conference, which is good. So you should think of it as some sort of guess for eigen. You want to find eigenvectors of a particular thing, like the transfer matrix or a Hamiltonian or something, which is very large. So it has a number of parameters probably going up, a number of components going exponentially with the size of the system. And Bethe ansatz makes that something going linearly with the size of the system usually, at least for the important states. So your guess will depend on a number of parameters, which are called the beta roots, and via all sorts of cunning and elegant arguments such as the algebraic Bethe ansatz, it turns out that those guesses will work provided this set of parameters satisfies these coupled equations called Bethe ansatz equations. And depending on your favourite lattice model, there'll be a different set of Bethe ansatz equations. But this has been formulated for very, very many lattice models. Not all. There are some situations where people still don't know how to figure out a Bethe ansatz. But very often this works. And so for the 6-vertex model, or the XXZ spin chain, the set of equations that crop up in sort of cartoon form look like this. Okay, so you've got k+1 things, E0 up to ek for the time being, and they have to satisfy this set of coupled equations where this Q, sort of what's called the anisotropy in the spin chain, is a physical parameter of the model. Okay, now strictly speaking, I've already lied because it's not actually -1 on that side. It's sort of something to raise to the power of the number of sites. But you can take a suitable limit in which it really is -1 on the right-hand side. You have to take the number of sites and the number of roots off to infinity, so keep track of one side of the root distribution. And that's actually the important limit for looking at things like corrections to finite size scaling for certain continuum limits of these theories. So it's an interesting limit, and in that limit this thing turns out to be -1, and that's the limit that I'm going to be able to make some connection to differential equations with. So we'll stick with that slight lie for the time being. Good, so that's Bethe ansatz. You've seen that. But one problem with that, it's kind of nice. You've reduced the number of parameters quite a lot, but still when you want to take something like a thermodynamic limit, you're going to have to take the number of roots to infinity, at least for states in regimes that you're often interested in. Okay. But luckily, Baxter came up with a different way of formulating the Bethe ansatz called the TQ relation. And he did this in the early 70s, actually not quite from this motivation. It was more like in the 80s and 90s that people really ran with this idea as a neat way of taking thermodynamic limits, people like Klumper and Peirce. But in the early 70s, he was trying to solve the 8-vertex model. And at the time, there wasn't a known Bethe ansatz for that, but he could still see that he could sort of run the analogue of what I'm about to tell you for that model, and that was kind of what motivated it. So this needs one extra piece of data, which is that the Boltzmann weights of these models depend on an extra parameter, spectral parameter it's called, and if you're doing the spin chain you have to sort of introduce this extra parameter sort of in some sort of generating function of conserved quantities, but for this spin chain, for this lattice model it's very transparent, so there's just this extra parameter in the Boltzmann weights, so your transfer matrix T becomes a function of that, and why that's important and why it's neat to parameterize these Boltzmann weights like that is because for different values of the spectral parameter these T's commute. So you've got a set of commuting transfer matrices which is kind of linked with the fact that the model is integrable, conservation laws, all the rest of it. Okay? And that means, since they commute, you can diagonalize them simultaneously. Okay, so the eigenvectors still depend on the spectral parameter, but the eigenvalues depend on the spectral parameter, but the eigenvectors don't, because you've diagonalized everything simultaneously. Okay, so now you've got a bunch of eigenvalues, these T's, and each of those is an entire function of the spectral parameter. And you want to exploit that. And what Baxter says is that the Bethe ansatz equation, so demanding that there are these Bethe ansatz equations, and then expressing T in terms of the solutions of those Bethe ansatz equations, is equivalent to demanding that T be such that there exists a second function Q, which is also entire, such that when you multiply T by Q, it sort of replicates itself twice, but at shifted values of the argument. Okay, and that's called the TQ relation. And the proof of that is rather simple. And basically what has to happen is that the zeros of these things have to talk to each other in quite a neat way to make all this work. Because when Q is at a 0, this side is 0, and then this side has to cancel.
Why should Q be entire?
Pardon?
Why Q should be entire?
Let's see it in a second. Well, it's a fact that Q, it's certainly crucial that T is entire. Yeah, no, it kind of, at least it's crucial in the way that I'm showing that it's true here. I agree there are some situations when Q is not entire, but for the 6-vertex model it is. Okay, there are some more complicated models where it's not, you're right. But I'm giving a sort of sketch here. So let's see it for this case, which is certainly correct for the 6-vertex model. So we suppose the zeros of Q are here, and because I've just said that Q is entire, then we can write Q as a product over its zeros.
You're restricting to the case of a finite.
So I'm just to keep the argument simple and show what's going on, I'll keep K finite for now. Okay, and as you can, if you really look closely at the bottom, you'll see that I've owned up to a problem about a potential problem when it's not. Okay, so we write it as a product over the zeros. We then put the spectral parameter in that TQ relation at the top equal to one of these zeros. Okay, so we've used entirety of Q in writing it like this. Now, of course, yeah, in situations when Q is not entire, you usually know exactly where the poles are, for example. That's one situation. Then it complicates life a little bit. But we're talking about ordinary TQ with periodic boundary conditions here. We don't need that. So we have Q, and then because T is entire, that 0 can't cancel against a pole, so the left-hand side really must be 0. So we've got Q of this is minus Q of that, or minus 1 is this ratio of Q's. Then you bung back in the factorized form of Q. It gets written like that, which gets re-expressed like that, and that's just the Bethe ansatz equations. So the punchline is that the zeros of Q, once the TQ relation is satisfied, the zeros of Q have to talk to each other via the Bethe ansatz equations. Okay, and that's just what comes out. And then from this formula up here, you can find out what T is, just by dividing through by Q, and that is indeed the correct formula for T in terms of the Bethe roots. So that's the essence of Baxter's observation. And obviously, in real situations when, for example, when K is finite here, then there'll be some funny little factors, in this equation that I haven't put down, and the Bethe ansatz equations will also have this little factor that I didn't write down, but in this limit that I'm talking about, everything works. The only thing you've got to be careful about is, of course, when you do take that limit, you've got an infinite product, and you should worry about convergence of that product. Okay, and that, if I had time, would be relevant to things like proving reality properties of various sorts of quantum mechanics problems, but I don't think I'll go into that now. TQ relation actually holds rather more generally in that sense than the direct Bethe ansatz treatment of these things. TQ is always true. And in fact, what Baxter did was he proved this TQ relation independently. So he proved it as an equation between matrices, transfer matrices, and then by taking its value on eigenvectors, he got this functional equation out. Okay, and then for the 8 vertex model, he didn't even have a beta ansatz to start with, but he still proved a TQ relation, and that allowed him to find out the equivalent of beta ansatz for the 8 vertex model. Good. Okay, well, there's another strand. So that was one set of functional relations, which powerfully constrains what's going on. There's another strand in all this, which is a set of relations called the fusion hierarchy. And this was also mentioned a little bit yesterday. So there's another thing you can do. So if you've got your 6 vertex model and you're trying to solve it, you can define a set of what are called fused transfer matrices. And there's lots of sort of clever stuff with representation theory behind this. But what these fused transfer matrices do is they then lead, when you act on eigenvectors, they all have simultaneous eigenvectors, just like all the different basic transfer matrices did, bunches of fused eigenvalues which satisfy another bunch of functional equations, which I've written down here. Okay, so we've got to think that T0 I'm going to set equal to 1, and T a half, so this half is a little bit like an SU2 spin, is equal to just the transfer matrix I'm really interested in. Okay, and then you can see this little relation here says that Tj spectral parameter shifted backwards, Tj shifted forward, is 1 plus a product of 2 other T's. Okay, so if you start off with these initial conditions, you can then find yourself a whole tower of fused transfer matrices and fused transfer matrix eigenvalues. Okay, well, in itself, that's not much good, because it doesn't constrain T. All I've done is define an infinite tower of new functions, and I don't know any of them. So you think, well, what's the point? Well, the point is that at special values of Q, in fact, at roots of unity, this hierarchy has a tendency to truncate. So you can show by some other arguments that when Q is a root of unity, then some T high up in the hierarchy will be forced to be equal to 1 and then the next one 0, just on sort of general grounds. Okay? And then you get yourself a closed set of functional relations again, okay, because you run out of unknowns in the end, and you've got the same number of equations as unknown. And then you can solve those equations. Okay? So the simplest case is actually when Q is e to the 2 pi I over 2n plus, well, 2n plus 3 I've put just for simplicity. So it's a simple root of unity. And then it turns out that Tn plus a half gets identically equal to 1. That gives you a closed bunch of equations, which you can then turn into a solution of your model. So that's an alternative way of getting to a solution of your model. So, what are the lessons from this?
But is this something simpler to solve than directly the vector equation?
It depends. So, well, I'll give a little bit of advertisement for this just here, I think. So two things to take from this. Okay, so if you've got TQ, an entirety of T and Q, that's the same as beta ansatz equations in some sense. Okay, so it's as constraining as the beta ansatz, which is very. Or alternatively, you could set up one of these fusion hierarchies, which would then truncate when Q is the root of unity. And either way, you get a closed set of equations, and you can convert those into these nonlinear integral equations that people talk about when they're solving these models. Okay, and if you go through route A, then you'll land on equations of what's sometimes called DDV or Klumper, Batchelor and Peirce type. Okay, or if you go down route B, you'll get equations of TBA type. Okay, in general. Okay, you might remember, perhaps you know that, say, in the Sine-Gordon model, the careful how you call it, but the DDV type equations actually depend continuously on the parameter, which is a bit like the Q that I had here. Okay, they all pop out the same, whereas the TBA type equations for Sine-Gordon actually flop about all over the place, and that's because of this truncation happening in different ways depending on the arithmetic properties of Q as a root of unity.
In Sine-Gordon theory, does this only work then at the second method?
The second method, you need to be a root of unity to get the whole thing to close, and then you get some horrendous.
It's exactly a threshold. One of those special.
No.
It's not the same.
No. Well, there are different thresholds around. Okay, so whenever Q is a root of unity, you'll be able to get something out. But what you get out can get very complicated.
But you're not saying that there's no TBA if there's no truncation.
Well, it would be an infinite. You need an infinite set of functions in general. It would be quite messy.
Here it sort of sounds like you need this truncation in order to find the TBA.
That's right. Yes. Well, in some formal sense, you could think about it as being an infinite set of equations that you get to some sort of limit or something. But yeah, in general, that's kind of correct. Yes. And what people sometimes, all the physical quantities depend continuously on this. So what you can sometimes do, and people do in other models, is you take a sort of discrete set of models at which the TBA looks nice, and then reconstruct the functions you're interested in once you know its values at a discrete set of points. This is something that's sometimes done. Anyway, so advantages of all this. Yeah.
It made it sound like there's always a unique Q, but you read about Baxter's Q74 and so on. What distinguishes the various Qs?
I think in this context, nothing. I'm talking about 6 vertex models. So these subtleties were all arising basically for 8 vertex model, I think. Okay, but I can't be 100% promise on that.
I mean, each model has a particular value of Q.
That's right. Yes. But you might want to solve a whole family of these things together. Okay. So anyway, no indices. That's good. So that was what Claudia liked yesterday. You've lost, in fact, you've lost a lot of sort of algebraic structure of all of this. You've lost signs of things not commuting and everything. Okay. And the number of beta roots, in some sense, in these final equations is more like a parameter. It's just how many zeros these functions have. And when you reformulate these things as integral equations, it kind of sits there very, very easily. So that makes thermodynamic limits very easy to take. And this method was used with a lot of success in the sort of 80s and 90s by people like Baxter, Klumper, Peirce, Batchelor, and then Bazhanov, Lukyanov, and Zamlodchikov. And what they did actually was they took this machinery over directly into the context of continuum field theory. Okay, so what I've sort of illustrated mostly for the moment is starting with a finite system and then taking a continuum limit. But actually you can define these gadgets directly in a C less than or equal 1 CFT, and that's what BLZ did, Bazhanov, Lukyanov, and Zamlodchikov. Okay, so in Hilbert spaces of C less than or equal to 1 conformal field theories, which is a continuous family of conformal field theories that they defined by some sort of free field realization, depending, so Q then is e to the I pi beta squared, and then the value of C that crops up from this is 1 minus 6 beta minus beta inverse squared, it turns out. Okay, so there's a continuous family of C less than 1 CFTs, and in general they're not unitary and they're not rational. Okay, but you can sort of dial up any desired value of the central charge less than 1 and any conformal weight for your basic field, okay, that you're talking about. So all the primary fields can be dialed up that way. But of course most of these primary fields won't have nice null vectors and so on. Okay? And then when this truncation happens, okay, so I said that at special values of Q things would truncate, and what generally happens there is that corresponds to places where you can restrict this, in general, non-unitary and non-rational theory, down to a minimal model. Okay, so there's a whole nice phenomenon about that where you can consistently restrict the space of states down to a smaller space. And once you've done that, you're left with a description of an honest-to-goodness minimal model. And the simplest example is, again, for those values of Q I told you about before, when actually it turns out that C is 1 minus 3 times 2n plus 1 squared over 2n plus 3, and that's the central charge of the minimal model M2 2n plus 3, which is kind of the simplest sequence of minimal models. In case you've forgotten, minimal models are always labelled by a pair of co-prime integers. So that's this whole sort of set of them. And if the two co-prime integers differ by 1, you've got the unitary minimal models, M, P, P plus 1. So if I get time, which is perhaps unlikely, there'll be a bit more about that later. Good. Okay, so the final sort of thing from this, which I've kind of almost said already, is that this TQ thing is so powerful, okay, it's so restricting that if I add in a little bit of analytic information about what this, say the location of these beta roots, say if I knew they were all on the beta on the real axis, then I might be able to pin down T and Q uniquely. So if I had another context where I got a TQ relation, I might be able to say that the functions that arose there were exactly the same functions as arose in the context of the 6-vertex model, or equivalently in the context of C less than or equal to 1 conformal field theories. Okay, well it will turn out that this will work for the CFT case. By the way, the CFT case that BLZ dealt with, it kind of from the point of the equations, this limit had already been taken, so all these factors were honestly 1 and so on. There weren't these fiddle factors to do with finite number of sites. Okay, so now I've got to get to the second bit, so yeah, that's bad news because I've used up half my time. But I'm on to part 2. So spectral problems for ordinary differential equations. So the place where these functional equations are going to crop up in certain equations are made by spectral determinants for these sorts of equations. So I'm going to sort of shoot through this a bit quickly, but I hope you'll get the drift. So we're going to think about a rather strange sort of cubic oscillator to start with. So I'm just going to treat one example and then show how it generalizes. So we're looking at a sort of typical Schrödinger equation that you try and persuade your undergraduates to think about, except that I've got a factor of I here, and the cubic power is a bit odd too in terms of putting boundary conditions on the entire real axis. Okay, so I want my wave functions to be such that they decay at plus and minus infinity, but I haven't got a Hermitian problem here. But it's a well-defined spectral problem nonetheless. And the claim is that this spectral problem somehow knows about a particular two-dimensional conformal field theory, and it's actually the one N25, which has got central charge minus 22 over 5. So that's the claim. We'll see that that's sort of true in a bit. Right, so I need to say a little bit about ordinary differential equations, and apologies to those who saw all this before when I gave talks on this before, but I think there's no alternative, as Mrs. Thatcher would say. So because we're looking at these boundary conditions at plus and minus infinity, a good way to analyse the solution to this equation is to look at what happens when x gets very big. Okay? That's our first thing. So the differential equation looks like this. That's what I showed you before. I'll call that bit P of x. And then the WKB approximation tells you what your wave functions look like. So for this particular case, it's just a simple calculation, and you get e to the plus or minus 2/5 times ix to the 5/2 as the behaviour of your solution at large x. So as x gets big, you get the situation I've drawn up the top there. Okay, so we don't really care about this algebraic factor, but as x tends to plus or minus infinity, one solution is growing in modulus and one is shrinking, and you call that a dominant and a subdominant solution. And even though there's a factor of I there, you've still got a bit of a real part going on, and so you do have a growing and a decaying solution. Okay, and the eigenvalue happens when your decaying solution that you start off with at, say, plus infinity manages to also be decaying at minus infinity. Then you've hit gold and you've got yourself an eigenvalue. And so in general that will happen a sort of discrete set of point values of E where the equation is such that that works. Okay. But try this, WKB doesn't give you everything, because WKB doesn't work exactly in this middle region where all the interesting stuff is happening. So you've got a sort of patching problem between your solution over here and your solution over here. And that's very badly drawn, but you get the general idea. Okay. So there are two things that people do in the trade. You can do some sort of asymptotic matching over zeros. When the WKB breaks down, when that P thing is 0. Okay? So you can do some sort of asymptotic matching to more complicated solutions, such as airy functions when it's a linear turning point. Or the other thing you can do, which is very elegant, is to think about things on the whole complex plane instead and try and sort of go from minus infinity to plus infinity by a sort of detour, which takes you all the time clear of this bad place where this P of x is 0. Okay, and then you can do some analytic continuation more easily, but it's still a bit subtle because of something called the Stokes phenomenon. Okay, so we're going to do that approach. So I'll sort of parameterize my x, which is where, so I'm initially interested in going off plus infinity here and minus infinity here. Okay, but I'm going to sort of skirt around this problem zone here by putting x to be some distance rho from the origin and an angle theta from the negative imaginary axis. Okay, and then WKB still works. There's no cheating there, and so you get that this function is equal to, asymptotically equal to e to the plus or minus 2/5, and then this little phase factor times this power of rho, which is now a positive real number. Okay, good. So that's reproduced here. Still keeping my eye on the time. Okay, so we've got that up here. Okay, and now there's a little mini sort of paradox you can worry about with this, which is that sort of general existence theorems and all the rest of it say that solutions to this first differential equations are actually entire and single valued in the whole complex plane. But if I look at my WKB solution here, then that's actually not single valued. If you go once around the origin and trace what's going on here, you don't get back to the same solution. Okay, think what the heck's going on there? Well, what rescues you is that the continuation, here's the buzz phrase, the continuation of asymptotic is not always the same as the asymptotic of a continuation. So what we've done is we've taken x off to infinity in one direction, and I've tried to continue that asymptotic around in theta afterwards. And you can't always do that. Okay, and the reason you can't do that is something called the Stokes phenomenon. So here's the Stokes phenomenon. So I'm sort of accelerating here slightly. So you can watch it on sort of slow motion action replay once it's on the web. We'll take a sort of closer look at what's happening here to try and understand this Stokes phenomenon. So we've got this complex phase here, and so far I've kind of told you that everything's all right because this phase here still has a real part, so we can still distinguish between a growing and a decaying solution. Right? But that ain't always true, and in particular as we sort of rotate ourselves around from plus to minus x-axis, we're going to go through places where this thing is purely imaginary. Okay, and then we lose track of which solution is dominant and which is subdominant. They sort of swap over. Okay, so those are bad lines. And actually on those lines, the eigenvalue problem isn't very well defined. Okay, so for an ordinary cubic oscillator, or actually for the upside down quartic oscillator, this actually starts happening on one or both directions of the real axis, which is why those are tricky. So that factor of I was actually good news from the point of view of making our eigenvalue problem well defined, because it meant that these lines where the things weren't well defined didn't mess us up on the real axis. Okay? These lines are actually called anti-Stokes lines for some reason. So let's draw a picture for our cubic case of what's going on here with the particular choice. Okay, so these red lines are the lines when I can't really tell a dominant from a subdominant solution. Okay, and they split the whole complex plane into sectors. And what happens is that even if you start, say, with a subdominant decaying solution here, when you continue it to here, you've now got a component which is growing and a component which is decaying. Okay? And actually, what Stokes discovered is that as you pass exactly the midpoint of this, your decaying solution is now so swamped by the growing solution that you could secretly change its coefficient without upsetting any sort of continuity or whatever. There'd be a little jump in the coefficient of the decaying solution because it's hidden underneath the growing solution. Okay, so that doesn't contradict anything you know about the asymptotics of the solution. But then as you continue around here, then of course that decaying solution suddenly turns into the growing solution again. And you've got yourself a different coefficient on the growing solution from the one you thought you would have done. Okay, so the solutions will reorganize themselves as you go around there. Each time sort of reorganizing themselves when they're hidden behind the other solution. And as you go around, that sort of patches everything up and makes everything continuous again. Okay, that means you've got to take this Stokes phenomenon rather seriously when you're considering solutions. Okay, and that's called the Stokes phenomenon. And actually this sort of patching everything up just right turns out to be equivalent to truncation of the fusion hierarchy that I told you about. So that's sort of nice. Right, well I think I'm going to have to skip most of the next little bit. But what you can do, so what I'm trying to do is to get some way of handling this situation. And the neat way to do this is to think about solutions which are subdominant in successive sectors. So here I've got 5 sectors which I've labelled S0, S-1, S1, S2, S-2. Okay? And I'll think to myself, I'll have a solution Y sub k, which is a solution which is decaying in sector Sk. Okay? So if Yk is subdominant in Sk, it'll actually be then dominant just by continuation in the neighbouring 2 sectors. But I don't really know what it's doing in the following 2 sectors because this Stokes phenomenon kicks in and I can't really tell. Okay. Good. Right, well I'll sort of save the little highlights of this, but I really think I'm going to run out of time to say much more about it. Right, well 2 neighbouring of these YKs, they're decaying in neighbouring sectors, and actually they have overlapping asymptotics. So one is decaying in one sector and then growing in the next sector, where that second solution is decaying. They cannot be linearly dependent because of that. Okay? So each pair of these neighbouring YKs, solutions which are decaying in neighbouring sectors, must be independent, and so a basis of a solution of this equation, right, is a second order ODE. Okay, so in particular, I could say that y minus 1, the one that decays in sector minus 1, is some linear combination of y0 and y1. And that's how you sort of understand this continuation in a neat way. So y minus 1 must be some constant c times y0 plus some constant c tilde times y1. And this is called a Stokes relation. It's the way of handling these things. And these c's are called Stokes multipliers. Okay, and the neat way to then figure out what these are is you just sort of take Wronskians. So remember what Wronskian is, fg prime minus f prime g, of these solutions with various of y minus 1 and y0 and y1 to figure out what these c's are as Wronskians. And these are not, so these are independent, the c's are independent of x, but of course they depend on e. E was a parameter in my equation. Okay, so these are functions of e, and actually they're entire functions of e just by general stuff about solutions of differential equations. Okay, and if you stare a bit carefully at this, you'll discover that actually if you normalize things right, then you can have c being just the Wronskian of y minus 1 and y1, and c tilde has to be equal to minus 1 in those normalizations. So I can sort of start to hint to you, though as I say, the details I think will get left behind. If you then rewrite this Stokes relation, which is just expressing the fact that I could write y minus 1 as a linear combination of y0 and y1, I re-express it in this way, and I've got that this Stokes multiplies c times y0 is equal to y minus 1 plus y1. Okay? And that looks very like this TQ relation. Okay? The TQ relation was T times Q is Q plus Q. Okay? And there are 2 problems with that. One of them is that I've not got the single Q here, but I've got y0, y minus 1 and y1. So I've got to get rid of this K, which is and also I've got this X here, which is also a bit spurious. Okay? Well, to get rid of K, you can actually do a sort of cunning little trick, which I think I'll have to ask you to think about later, which is that you can define YKs. Once you've got a solution which decays in one sector, you can sort of shift X and sort of move it round to be a decaying solution in the neighbouring sector. And that almost works, except that then you've got the value of E wrong once you've changed the variable. So you compensate that by shifting X by shifting E as well. Okay, so you think of Y of X and E as a solution of the equation in X for a particular value of E. And if you take the equation with a slightly different value of E and also shift X, you get yourself a solution that decays in the appropriate sector. Okay? So once you've done that little trick, you've got yourself an equation of C times Y0 is is something times y0 plus something times y0, where now we're shifting e as well as x. Okay, we've still got x in the way, but that's fine. We just set x equal to 0. So now, I'm really not going to get time to get to the junk food, but still. So now our relation looks like this. C times d is d plus d, where this function d is just my basic solution y0, which was a solution which decayed in sector S0, evaluated for that particular value of e at x equals 0. Okay, and that's exactly on the nose the six vertex TQ relation of the sort we saw before at the value of q. So you've got to keep track of, oh, I didn't say terribly clearly what omega was, but omega was the thing that sort of dialed you round from one sector to the next. Okay, so it actually turns out this corresponds to the value q is e to the 2 pi I over 5. Remember, there were 5 of these sectors going around the origin. Okay, so that's where this value of q came from here. Okay, and you might object that there's these factors of omega. Well, that's actually in the integral model world related to this twist that Volodya was talking about yesterday. So you can define a slightly more general version of the 6 vertex model where there's a little twist, and then you get these little phases which crop up as well. So that's fine too. You've got a particular value of the twist there. Okay, and now both of these functions, c and d, you can reinterpret. So now we're thinking that c is actually t, which way around it is. D is t and c is q. Is that the right one? Yes, that is. You can think of those as spectral determinants. Okay, let's just pause for a moment to see why that's true. Because C, right, was the Wronskian of a solution which decayed in sector -1 with a solution which decayed in sector +1. Okay, if a Wronskian vanishes, then those two solutions of the differential equation are proportional to each other. Okay, but this one decayed in this sector and this one decayed in that sector. So they're proportional to each other. You have a single solution which decays in both sectors. That means you've got yourself an eigenvalue. So the zeros of this C are exactly the eigenvalues of this funny spectral problem I told you before. And this D, okay, well that vanishes if and only if this solution which decays at -infinity is also zero at the origin. And that's a radial spectral problem where you you specify your eigenvalue problems by a decay condition at infinity and one at the origin, which is also rather natural. Good. So I sort of was aware this was going to be a problem when I wrote the transparency. So it says conclusion, but it also says conclusion to this bit. Okay, so but it's okay. I mean, I've kind of got to a punchline, so I'll just rabbit on for the rest of my time. So this is kind of, in some sense, the main punchline anyway. So q is equal to e to the 2 pi I over 5. These t and q operators that BLZ defined, which are encoding properties, I mean, in fact, these t's and q's encode all the conserved quantities of the conformal field theory at this particular point, this particular conformal field theory, actually also encode spectral data for this complex cubic anharmonic oscillator, which is a very strange connection, and in fact is practically quite useful because computers are quite good at solving differential equations. So evaluating spectral determinants like this is quite easy on a computer. It's actually a real alternative to doing Bethe ansatz for these systems, and people are using this now. They've got various funny condensed matter problems, and they actually use these differential equations to try and get data out from them rather than directly solving Bethe ansatz. Okay, and this is beta squared is 2/5, remember q was that, which is c, if you translate it down as -2205, which is what I said it would be earlier. So I've sort of justified, but at some speed, what I said before, and that says 5 minutes. Right. Okay, so small generalizations of all this. Well, we could replace this potential, which was ix cubed, right, by ix to an arbitrary power. You have to be a bit careful when n is a real number in general, then you have to put a sort of branch cut in, and actually everything now lives on some spiral cover of the complex plane. But all the arguments I gave basically just go through, and then you get all other values of q. So you get this whole family of different values of c just by dialing up what the value of m is there. Okay? You can also add in an angular momentum term at the origin. Again, everything sort of works. You've got to be a little bit careful about how you set x equal to 0 now, but you can still do it. And this was pointed out by Belovin, Lukyanov, and Zamlodchikov shortly after Roberto and I made the first observation. And that actually gets other sorts of twisted boundary condition, which corresponds to looking at other Virasoro representations. Okay? So the punchline of all this is that this simple ODE actually contains the full continuous family of C less than 1 CFTs continued by BLZ, and all of the primary fields in those theories, just by dialing up L right.
So how do you make c equals 1/2 here?
C equals 1/2? Well, you've just got to go back to that formula about 1 minus 6, beta minus beta to the minus 1, figure out what the value of beta should
So
be.
it should be something nice, right?
Yes, sorry, yes, that's exactly right. Good question. So m equals 1 is the answer. It just turns into the ordinary harmonic oscillator. Yes, that's one nice thing. And actually the other nice thing is this point delta equals 1/2 that's been mentioned where you get this fancy links with combinatorics and so on, corresponds to n equals to a half, when your differential equation just has x minus e in it, and then sort of the e sort of can be absorbed. Right.
And the limit and c equals 1, there should be some
Yeah, c equals 1, if I'm remembering it right, it's which way up is it?
potential becomes logarithmic.
You end up with a sort of square well in one limit. I'm just trying to remember. That may be actually the classical limit of c tends to minus infinity.
Equals 1 and c.
Yeah, no, I think you're right. Yes, I think it's you end up with some sort of. You have to also think about how you take the limit, but I'm melting down in terms of time left, so I'll think about. I'll talk to you about it later. Okay, so the one thing we don't get, so at least I'm going to mention the problem that we've tried to address in this later paper, if not actually tell you the solution really. The one thing we don't get to see is any special role for minimal model. We've got this continuous family of things, but we don't actually see where the minimal models are special. Well, there's actually a hint from this, from truncation. So I'll tell you how truncation works in this, and then I think I'll have to stop. So remember we had these fused T operators, and I told you that when this fusion hierarchy truncates, then you're in a situation corresponding to a minimal model. Okay. Well, it turns out that these fused T operators are terribly natural from the ODE as well. Okay. So they're again Wronskins, but you don't take Wronskins between next to nearest. So the Wronskin we had before was y minus 1 and y1. But if you click yourself around a bit further, then you get these fused T operators instead. It all works out very nicely. So here's the picture. So T itself was T a half is the Wronskin between these two. So I'm taking the cubic case again, the Wronskin between these two. And T1, you've then got to click yourself around one more slot. And then T3 halves, you've got to click yourself around two more slots. Okay? And you evaluate these Wronskins, and you can prove that by sort of consistency of Stokes multipliers around here, that this is exactly the same as the fusion hierarchy relations. Okay? But now we can understand truncation. So if you look at this last one here, for this particular situation, everything's analytic, so no one told us we had to take this contour around here. And we can deform the line along which we're considering our wave function, which is how we're thinking about this, to go here instead. And now we realise that what we're actually talking about here, sector 3 is actually the same as sector minus 2, counting round the other way. So we've actually got ourselves two neighbouring solutions. Okay? And I already showed you earlier, though it went by way too quickly for you to realise, that actually Wronskins of neighbouring solutions are always trivial, okay, because they're sort of overlapping WKB asymptotic. So actually what we've proved from this is that indeed for Q is 2 pi I over 5, then this fused transfer matrix T3 halves is equal to 1, without doing any of the sort of fancy representation theory that people normally have to do to get this. We've got it directly from this alternative interpretation via differential equations. And that's exactly right for the integral model world. So, I'm aware of the time, but not doing very well with it. So, let's see how we go. I'm almost to some sort of vague punchline, I think. So how do we generalise that? Well, you can sort of see that if 2m was an integer and LL plus 1 was 0, everything would be fine. Okay, we could do the same thing. You just have to click yourself more notches round the origin, and then you could peel the contour off again and get yourself the thing truncated. So that was the thing that we spotted a long time ago. But if 2m's rational, then you should think the thing lives on some sort of spiral cover of the complex plane, which then collapses, truncates at some point to a finite cover. Okay, so you think that some sort of truncation might again be on the cards. But it's all a load more subtle, in particular because this value of, because L you might want to preserve there. And there's some funny monodromies going on around the origin too, and these can sort of interfere with everything. Okay, good. And I think I know I'm honestly out of time. So all I'll say, so the question you should ask yourself now is, helped by the sort of gale that's blowing around there. So you should ask yourself, is there some better way? We can't really handle the monodromy terribly well with the equation like this, okay, to see the truncation for general rational values of 2m. Well, it turns out that there is, and that's what we talked about in our recent paper. So what you can do is you can take a variable change which sort of unwinds this now finite cover of the complex plane, and at the same time gets rid of L when you're talking about the ground state of the minimal model, okay? And then you fall onto a much simpler equation, which I'll flash up just quickly. So you fall onto an equation of this form here. It's not saying, oh, it is saying stop now, damn. Okay. So you fall onto that equation there, Okay, and you can see it's a sort of generalized eigenvalue problem. So you've got now E doesn't appear on its own, but multiplied by Z to the A minus 2. So if A is equal to 2, then it's an ordinary eigenvalue problem, and that's the cases of the simplest truncation. But for higher values of A, it's a slightly more complicated problem. But we've got rid of all this nasty monodromy now. Everything is obviously truncating fine. And the final thing to say, so this is honestly the final thing, is that that was for one very special primary field when I chose L appropriately to get the ground state of the minimal model. You can now say to yourself, well, let's think about other values of L and see whether we're still allowed to have zero monodromy. And it turns out that you are, okay, but the values of L that you're allowed are restricted to a finite set. And actually you get that finite set by solving a sort of simplified version of something called the McNugget problem. So that's the connection with junk food, okay? And that exactly spits you out the CAPS table of the minimal model corresponding to the thing you're thinking about in terms of the allowed values of L. Okay, but I'm afraid I have no time to tell you about that, so you'll have to have a look in the paper. But at least I got to the junk food, so I can stop now happy.
One quick question, I think.
I remember that John Cardy showed that the sort of Landau-Ginzburg effective theory to describe this M=3 model is some scalar field with a cubic, purely imaginary cubic potential. Is this just the zero mode of this?
I don't know, and it's intriguing to think that there might be some better connection working here.
It looks like the zero mode.
Yeah, but but Cardy's argument is sort of an approximate argument, as far as I can tell you. It's sort of semi-classical intuition. I think
That's a conformal point.
Sasha Zamolodchikov had a similar argument based on equations of motion. But I don't know how to make that into a concrete connection. It's intriguing, though. It is kind of striking that, yeah, it's a cubic point as well. Yeah, and I think that generalizes actually as well to the point, if I remember right.
Okay, let's thank the speaker again.